أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. The theme of today's lecture is to discuss the kinetic theory of ideal gases. This lecture has been taken from the course outline of Thermodynamics, having the course code of PHY331. In today's lecture, we will basically understand the microscopic approach about the ideal gas. Some of the basic points of the kinetic theory. Basically, the microscopic point of view regarding the classical thermodynamics is a bit different. If we see, classical thermodynamics is entirely macroscopic, that is, depends on large measurable values. Looking toward the first law, it could be expressed in the form of a relationship between the work, heat, and internal energy of the system. Similarly, the specific heat at constant volume of the hydrostatic system could be calculated from the internal energy of the system, which is a function of temperature and volume, and that is given by Cv is equal to change in internal energy with respect to T when the volume is constant. So the heat transfer during isochoric process could be calculated from the detailed information regarding the U and Cv. That could be written as that Qv is equal to Cv dt integral from Ti to Tf. So the classical thermodynamics fails to provide detailed information regarding the U and Cv. So we need to develop the equation of state for a question arises how we can develop the equation of state for any particular systems. So there are two microscopic theories which are presented to deal with this problem. The first one is the kinetic theory of gases and the second one is the statistical mechanics. Kinetic theory deals with the particles, its internal and external motion, their collisions with one another and with the walls of the container, and the forces of interactions, while statistical mechanics avoids the mechanical aspects and deal with the energy aspects of the particle based on the statistics and quantum mechanics. So we need to discuss the kinetic theory of ideal gases that was developed in early 19th century. Regarding the kinetic theory perform work by Avogadro and Lossmith. So in this case we need the calculation of number of atoms or molecules in the molar volume is the basic of kinetic theory of gases. We need to know the number of atoms or molecules that are present in a molar volume of a given gas. So temperature in this case is a function of the motion of the particle of a gas, and chronic is also the originator of the kinetic theory of gases. So for monatomic gases, microscopic theory of gases is based on the assumption for the behavior of atoms of ideal gas. So say for example, if we have a small sample of gas that consists of n particles for a particular sample, then the atoms are identical and inert. For mass m of each particle, the total mass is mn, denoting the molar mass m, that is actually expressed in kilogram per mole. So the number of moles are given as n is equal to m capital N divided by capital M. So Avogadro number is the number of particles per mole of a particular gas, and that is equal to Na is equal to capital N divided by small n, R is equal to capital M divided by small m, and its numerical value is 6.0221 multiplied by 10 to the power 23 particle per mole. So a mole of an ideal gas at freezing point of water and a standard atmospheric pressure occupies a volume of 22.4 multiplied by 10 to the power 3 centimeter cubic. So normally the number of atoms in 1 centimeter cubic is 3 multiplied by 10 to the power 19 atoms If we look toward the cubic millimeter, so the number of atoms in that will be equal to 3 multiplied by 10 to the power 16 atoms. And looking toward the cubic micrometer, the number of atoms will be 3 multiplied by 10 to the power 7 atoms. So atoms of the ideal gas are like Hertz sphere in perpetual motion, which are randomly moving. So with normal temperature and pressure, the distance between neighboring atoms is greater compared to the size of the atoms. So the diameter of the atoms is 2 or 3 multiplied by 10 to the power minus 10 meter. So in standard condition, the distance between atoms is 50 times greater than its diameters. So atoms of the ideal gas exert no forces on each other except when they collide each other or with the walls of the container. During the collision or between the collision, they move with uniform rectilinear motions. So the collision between the smooth walls and the atom is perfectly elastic, and only the perpendicular component of the velocities change upon collision. So the absence of external force, the atoms are uniformly distributed throughout the container. So the number density is, that is actually number of atom per unit per volume, is assumed to be constant quantity, and dn is equal to n divided by vtv. So there is no preferred direction for the velocity of any atoms. At any moment there are so many atoms moving in one direction or another. So the atoms are moving with different speed ranging from 0 to the speed of light, and the total momentum is equal to number of atoms of speed small w in solid angle d sigma, and fraction of these atoms striking dA and time dt, and change in momentum per collision. So this is some equation what we get for the total change in momentum of these particles. So change in momentum per unit time per unit area due to collision from all direction in the pressure Tp exerted by the walls and d and gas atoms. So what happened? We can get the equation for this change in momentum per unit time, that is equal to dpw is equal to m w square dnw divided by v, and the whole value which is like 1 over 2 pi integral 0 to pi d phi, and again integral 0 to 5 over 2 cos square theta sin square theta d theta whole. So that is the value or the change in momentum. So the total pressure due to atoms of all speed could be written as that PV is equal to 1 over 3 m 0 to infinity w square dn w. So average square of the atomic speed could be written in this value, and from that we can get the PV value, that is equal to n small m divided by 3 w square average. So from that we can get the PV value, and further we can compare with the ideal gas equation, that is equal to P is equal to nRT. So when we compare both the equations, so the left side of the equation is equal to each other, so the right side of the equation will also become equal to each other, and we will have n small m divided by 3 w square average is equal to nRT. And if we solve the same equation for t, then we can get the value of t is equal to 2n divided by 3n r 1 over 2 m w square. And this is actually the interpretation of temperature based on kinetic theory of gases. So temperature is proportional to the average kinetic energy of the atoms in the ideal gas. So how we can interpret the internal energy in the term of it? So the internal energy could be written as a U is equal to 1 over summation 1 over 2 m w j squares, and that could be further multiplied in these forms. So if we have monoatomic gas, then the internal energy is further simplified as, and it is equal to U is equal to 3 over 2 nRT. So the internal energy is proportional to the thermodynamic temperature only, and it is found consistent with the experimental data. and the value is given as U is equal to 3/2 N divided by NART, or that is equal to 3/2 NKT. So average kinetic energy per particle is equal to 1/2 m W square average is equal to 3/2 KT, and the energy per atom is equal to 1/2 mv square mv square into average. So if we compare the values for the value of different thermodynamic systems, so that could be written as, if we have then there is different expression that is used for the, in case of classical thermodynamics and in case of kinetic theory. In statistical mechanics, there are different sort of interpretation used for that, and different ways are used to calculate the values of something. So comparing the interpretation or the description in thermodynamic and kinetic theory, we have this table. Here we have small m represent the mass of the system, and in case of kinetic theory, if we use the word small m, it represents the mass of the particle. If we use small n in thermodynamics, it means the number of moles of that particular gas or sample, where capital N describe the number of particles in case of kinetic theory. If we have small m, that is used as a mass per mole, or that could be further simplified as a m small m divided by n small n, that is the ratio, that is actually molar mass or molar weight. So in comparison, we use in kinetic theory the words Na, that is actually Avogadro number, and the Avogadro number is the number of particles per mole, and that could be written in the form of equation that capital N divided by small n, that is Avogadro number. And in case of thermodynamics, we have molar gas constant that could be represented by R, capital R. But in case of kinetic theory, we have another constant, that is the Boltzmann constant, and the Boltzmann constant is equal to capital R divided by Na. The volume both in thermodynamics and kinetic theory is represented by capital V, and that is same in both cases. And looking toward the density, so the density is a bit different in both of it. In case of thermodynamics, the density is represented by rho, that is actually the mass density, and mass density is actually the mass per unit volume. While in case of kinetic theory, it is actually the number of density, and the number density actually describes the number of the capital N divided by V. So this is something that describes a comparison between the classical thermodynamics and kinetic theory. And the kinetic theory basically provides the microscopic explanation of the same phenomena that as you use in thermodynamics. Further detail of the microscopic approach could be obtained from the statistical mechanics. So this is some comparison. So the equation of state for ideal monoatomic gas is equal to PV is equal to NKT, and that is the equation of state for it. So this equation of state could be obtained from the, here in this case, just like PV is equal to nRT, and that is obtained when we are calculating the internal energy of the system. As we were discussing that the two values are a bit different in kinetic theory. One was the actually the change in momentum, that was the total change in momentum, and one was the temperature, and the equation for temperature was obtained from the equation for temperature could be obtained that describes that how the temperature depends on different factor, and from that we can get the equation of temperature that it depends on various factors. And the other thing was, this is the equation of temperature, capital T is equal to A2N divided by 3NR 1/2 mW square, and that is actually the interpretation of temperature based on the kinetic theory of gases. and from this equation it is clarified that temperature is proportional to the average kinetic energy of the atoms in the ideal case. So the other thing that was important along with the temperature, the other thing that was most important describing the idea, the interpretation of the system was the kinetic energy, and we have developed the equation for the of the kinetic energy from starting from the basic equation of kinetic energy that was equal to the summation of each particle, the summation of number of particles, that is equal to 1 over 2 m kinetic energy of the particles, summing the kinetic energy of the particle, that was equal to 1 over 2 m wj square, and that was further simplified, and at the end we compare the same kinetic energy what we obtained are the value of PV from this equation with the ideal gas equation. From that ideal gas equation we have developed the equation for the kinetic energy of the particle. So the most important thing here what we obtain is the equation for the kinetic energy, and that is equal to U is equal to 3 over 2 N divided by Na RT, and that is further simplified is equal to, that is equal to 3 over 2 nkt. So this is something that is describe the dependence of internal energy on these factors. So the internal energy describe that this equation actually describe the internal energy of the system in term of the kinetic theory of gases. So further, so these are actually the two factors that could be described from the kinetic theory of gases. One is the temperature, then it depends on various factors, and the other thing is the internal energy of the system. So both internal energy and temperature are the most important factor that could be expressed in terms of the microscopic parameters, while the classical thermodynamics has expressed both value in different perspective. So this kinetic theory based on few assumptions that was discussed in the beginning of this kinetic theory. Just like the first assumption was that that each small particle gas consists of Avogadro number of atoms, particular sample of gas consists of particles. So there are some assumptions for the kinetic theory of gases, and we have normally many assumptions that describe the basics of kinetic theory of gases. So the first assumption were actually the number of atoms in a molar mass. So that could be described by the Avogadro number, and that is actually the number of particles per moles of a gas. So Na, capital N is equal to NO. So from that we can calculate the how many number of atoms are present in a unit volume. So further description has been given regarding the size of the atoms and the distribution of the atoms, in which it is said that the atoms are like a heart sphere, and that are moving randomly. So the gas and the diameter of this atom is 2 or 3 multiplied by 10⁻⁻10 meter. So in normal standard condition the distance between atom is 50 times greater than its diameter. So some of the other assumptions that are the most important assumptions are regarding the atoms of the ideal gas, that is a bit simplified, in which it is considered that it exerts no force on each other except when they collide each other or with the walls of the container. So during this collision what happen? They exert force on each other, but between the collision they move with uniform rectilinear motions, and between the collision when the same particles are colliding with the walls of the container, then it creates pressure, and that pressure could be obtained from this particular equation. So if there is no external force, then the atoms are uniformly distributed in the container, and the density of atom is calculated. So these are some of the simplified assumptions of the kinetic theory of gases that lead to the calculation or getting the values of most important parameter, that is the temperature, the interpretation of temperature based on the kinetic theory. And the other thing is, most important thing is the internal energy of the systems that could be described. So this is something discussion about the kinetic theory of gases and their interpretation of some values based on the kinetic theory of gases. So thank you very much for now.